Thanks for coming back. So let's continue with the 7th session of the part 1 of Nonstationary Time Series Analysis with modern signal processing techniques. Okay. Well, so the topic today is in this session will be ridge extraction. What is ridge extraction? Actually, this is the key step to transit from the above theories to practical applications like decomposition, denoise, feature extraction, or the base, which is the base of learning, or so on. Why? Why do we need it? The main reason is the only thing I gave you so far is something so-called ideal time frequency representation, which is a function or a distribution over a two-dimensional space, or just an image. In practice, where is the instantaneous frequency? What is instantaneous frequency? Sorry, we do not know. We do not know instantaneous frequency of each component yet. So without knowing this information, we cannot carry out the reconstruction formula I showed you before. So intuitively, what is a ridge? A ridge is a sequence of local maxima of the time frequency representation along the time index frequency axis that satisfies some regularities that is associated with the instantaneous frequency of an intrinsic mode type function. Often, it is visualized as a curve on the time frequency domain. So let's take a look at this example again. What I showed you before. You can see there are two curves, right? And these two curves, as I told you, the intensity over a time frequency domain indicates the strength of the oscillation. So locally, the maxima is over the curve. And suppose we just link all those curves together. This is called the ridge. Let's call the ridge. And please don't get confused of this ridge extraction with the ridge commonly used in statistics. They are related. And the ridge extraction problem we are talking about here is a subset or a very special case of the ridge problem or ridge detection in statistics, which is on a more general setup, but we focus on the two-dimensional domain with under the ridge we have some specific structure that is indexed by time with the value in the frequency axis. So there's a very specific, very spatial type of ridge. So algorithmically, what we do is very simple. We will take the discretization of synchronous squeezing. Okay, we do some normalization. And we try to fit a curve, a vector, in this case, after discretization, C, so that at each time in the frequency axis, the energy is maximized. But we also want to control the regularity, saying that the difference or the differentiation is not too large. So we'll control, this is controlling the largest, to find the largest amplitude entries in the time frequency domain with some regularity. Where lambda is a parameter, you can choose when you apply it. And the C star as a vector, if you look at this time frequency representation discretization, it will be kind of a set of points that indicates the location of the ridge. And the theory tells us that the C star at time j, if you multiply by the frequency discretization bin size delta eta, then that will be roughly the instantaneous frequency, or this is VL prime, instantaneous frequency at time j times delta t, where delta t is the time domain discretization size. So this is an overall curve extraction or ridge extraction algorithm to get instantaneous frequency. The implementation is very easy, just by some research. And in the code I shared with you, there are several different implementations that you can play with. Again, this is actually a big, well, I shouldn't say a big field, but many people work on this, and there have been many papers back in 1997, even up to now. Recent paper 2023. People try different approaches to get the ridge in a reasonable and rigorous way. And this is what I meant by the general ridge detection literature in statistics. I only show you one. There are a lot, tons, maybe 100 papers in statistical literature for ridge detection. But we are doing not really ridge detection, we have ridge extraction in time frequency analysis. Okay, so overall, this is an illustration. I give you a noisy data with the clean underlying signal. You run synchro squeezing, you get 3 curves. You see 3 curves by eyes. That is what you have. Then you run ridge extraction algorithm, you get these 3 curves out. And these 3 curves will give you the instantaneous frequency information of each component. And certainly, if you have multiple components, the ridge extraction algorithm I showed you here in this algorithm will only give you 1 curve at one time. So you have to iteratively run different steps to get each curve. Okay, or there are some algorithms that you can get multiple curves at one time, but you need to find a way to arrange them. We will not go into details of this, of all existing algorithms, but you know the basic idea. That is something we need to do. So the benefit of squeezing, okay, in ridge extraction is the following. It can enhance the accuracy of curve extraction. It can ease the way you fine-tune the parameters, you determine the curve, and so on. And it will hence enhance the accuracy of decomposition. There are some papers that discusses this kind of behavior from a more engineering perspective, which you can consult if you have interest. And then we can combine different things. For example, we have the reconstruction properties, we have robustness properties, we can do curve extraction. Then let's take a look at the combination. Again, we have 3 components, 2 components, or 3 components, and this is the trend, and this is a signal. And now I add some non-stationary noise to it. So you can see the first part is noise is larger. The second part, noise is smaller. So this is a non-stationary noise. And now I run synchro squeezing. This is the result. You can see 2 curves. So far, so good. And then you get curve extraction, and you find 2 bands. And over each band, you just run the reconstruction. Oh, this is phi L prime, not phi L. This is phi L prime. It's a type. Instantaneous frequency phi L prime. Then you get the result. The red one is the ground truth. The black one is the reconstruction. So considering the noise, the reconstruction, I would say, is not bad. And you can also reconstruct the trend by focusing on a low frequency region, or even do just local trend, local median, local mean approach, and so on. And if you subtract these 3 reconstructed one from the noisy signal, you can get the noise. And the ground truth, and the ground truth is the red one, the reconstruction is the black one. So in this sense, you get the desired decomposition. As I mentioned on the blackboard before, after you get each component in the complex form, You can take absolute value and phase to get the amplitude, modulation, and the phase of each function. And there is a very important small detail here. That is, from here you can only get instantaneous frequency, but how to reconstruct the phase? It is not that you can just do a direct Hume sum to get a phase, because you do not know the initial phase. That is, you want to apply integration of a derivative of the function, you need to know f of 0. But in general, you don't know the initial phase if you only have instantaneous frequency. So reconstructing the phase from a complex form is slightly different from getting the instantaneous frequency. So getting instantaneous frequency is a kind of a hinge point. Once you get it, you can get everything. That is why ridge extraction is important. So, looks good, right? But is this the best way for reconstruction? Usually I would say no. There are several different ways, and people are discussing which is the best, which is a better way. For example, one way you can consider is use short-time Fourier transform for reconstruction. You can first get a ridge in synchro squeezing transform, and then you use the ridge in synchro squeezing as the guide to determine the ridge in short-time Fourier transform, and then you use the ridge in short-time Fourier transform for reconstruction. There are several variations. Which one is the best? To my knowledge, there hasn't been a systematic comparison, but there are several ideas which we can consider, and maybe some is better than the others, but we usually fix to one and apply it. We will come back to this to details of this issue later when we focus on the decomposition. Right now, we have some very simple decomposition, but later on we will focus on more detailed decomposition mission. Very good. So now we know the ridge extraction, and we have some basic properties of synchro squeezing. So this should already give you a global picture of how synchro squeezing can help you in signal processing. But what I haven't answered you is the following question. In practice, there is always noise, and noise generates uncertainty. And once you have uncertainty, you want to quantify the uncertainty. And that is usually a statistical work. That is, we want to do some statistical inference. Okay, or people may call it an uncertainty quantification, UQ, which is a kind of hot topic nowadays, but turns out it is nothing but trying to understand more about the distribution of the statistics you have interest, or the mission you want to do, what is the uncertainty. So we continue with the second topic about statistical inference by synchro squeezing, and we will try to answer some questions about, hey, if now you have noise, simply a Gaussian white noise, and you apply synchro squeezing to it, then what will be the distribution you have? What does it even mean? Okay, so let's focus on this very simple model, which is a very, very specific adaptive harmonic model. That is, we have only one component, and the amplitude is fixed, frequency is fixed. So this is a very simple harmonic function. And we have noise, and this noise is a stationary generalized random process, and we assume white Gaussian for simplicity. In the paper published in 2013, this year, in Annals of Statistics, you can see more general random process as noise. Let's focus on stationary generalized Gaussian random process as the noise. And we use a generalized because we discuss everything in a continuous setup. And if you do discretization, after discretization, this is nothing but a white Gaussian noise. And when A is 0, that is, there is no signal, no oscillatory signal, then we call the model to be null setup. There is no signal, but only noise. But If A is not 0, it's called non-null. And a common statistical question you may want to answer is, fine, you have a signal, A is non-zero. But if A is 10 to the minus 1 billion, super small, is it possible you get anything out of it? But if A is very, very large, so large that the noise is relatively small or neglectable, do you need to care about it, right? If noise is super small, like 0, or even smaller than the machine tolerance, machine epsilon, then you can ignore it, right? But the question is, what's in between? What's in between? How strong is the signal? How strong the signal is so that we can detect it, or we can say something. That will be the question. But to answer that question, the first question we need to answer is, what is the distribution of synchronous squeezing transform? Okay, you have recall this is the full version of the synchronous squeezing transform. Here I do not use delta. I write down precisely 1 over alpha, the Gaussian approximation. And we want to ask, okay, what is the distribution of this guy? Now the question is, you have an integration, but how to achieve an integration or how to study it? So what we proposed before was, let's do some discretization in the frequency domain. Okay, we fix a time t, and we discretize the frequency domain using the grid delta eta, and we run Riemann sum. And now the question is, suppose I give you this quantity, and let n goes to infinite and delta eta goes to 0. Okay, we will use this guy to represent sy in the continuous setting. So now the question is, what can we do? To approximate it, we will denote this whole term as y alpha eta c eta. Because c is the targeting frequency, eta is all frequency we have interest in the short-time Fourier transforms frequency domain, and alpha is is approximation or we call resolution. And you can do some simple calculation, which tells you that if the two frequencies are sufficiently far away, then the covariance of this term with different etas will be exponentially small. So this suggests us that while we cannot directly apply central limit theory over the set of random variables, because there is a still dependence, but the dependence is small. So suppose we are able to approximate this random variable by some m-dependent random variable sequence, random variables, then we can apply central limit theory. That's the basic idea. So how to construct an m-dependent random process that approximates this guy? Then what we do is very simple. We just truncate the window. Once you truncate the window in the frequency domain, then in the frequency domain, the short-time Fourier transform and the reassignment rule will be independent after m for a carefully selected m, so that we can apply central limit theory, m-dependent central limit theory. So the main theory we have in the end is the following. Suppose this rho is less than 5. This is actually controlling the noise colorness. And in our case, forget about rho, we don't need it. Okay, and the fix c greater than 0, and take a small delta, and set beta in this way. And then you set the discretization in the frequency domain in this order, which you see a bit, right? This is square root of NO. which means you will have square root of n, or you will have more n points in the frequency axis. Then in the frequency axis, the scale will go from 0 to square root of n. So you will cover the whole frequency region at the rate n half plus theta. So now assume alpha, which is a resolution in the synchronous squeezing transform, satisfies some basic condition, that is, it will go to 0, and it will be of order 1 over n. That goes to 0. Then we have the following. The synchronous squeezing transform, okay, will converges to a complex Gaussian random variable with covariance, with the variance nu and the pseudo covariance p. And that tells you that everything we get, technically in the end, well, not technically, everything we get in synchronous squeezing, although it's very nonlinear and looks very crazy, but in the end, it is Gaussian. It is Gaussian. And this gives us a lot of benefits when we design statistical quantities or design algorithms, which I will show you in a bit. And the result I showed you was about synchronous squeezing in a continuous setup. What about in practice? We have some discretization. And what we showed in the paper is the same. If you do some discretization of the signal in the time domain, then in the end of the day, the discretization will converge to the continuous setup without any trouble in probability. So discretization doesn't hurt us. That is essentially what it tells you. But you need to be carefully design how to do discretization. Okay, and for example, we have square root of n here and so on. So this is a simulation, and the blue curve is when you have just purely noise input as input. Then you can see, compared with the standard normal quantiles, it is just a 9, which tells you it converges to Gaussian distribution. This is Q2 plot. And if you have non-null setup, that is, you have an oscillatory signal at 10 Hertz. Then you can see when consist 2, it is the same. The gray line is like Gaussian. 6 Hertz, gray line, and the center at 0, the same. Center at 0, the same. But if you now go to C10, which is the frequency of the oscillation, then you can see it is also like a diagonal curve, but it has a different mean. But it is still like a Gaussian. And those are with different alphas. So it tells you that we do get Gaussian distribution, which is nice. So once we have some distributional result of synchronous squeezing, if time permits, I will give some proofs later. But you can read it. The proof is kind of tedious. But so what can we do? Now we want to ask the following question. This is the signal that you can read by your eyes, right? That's oscillatory in the beginning, but after a while here, it starts to behave weird, and then here it doesn't seem to oscillate, or it oscillates in a way very different from PPG signal. This is its synchronous squeezing transform. You can see a very dominant curve in the beginning, and then after a while it becomes blah, 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 blah. So the question we have right now is, can we detect when the signal is oscillating or when it doesn't oscillate? And this is a bit like the change point detection problem, but we haven't touched the change point detection. Change point detection, we will discuss it later. Here is just oscillation detection. Okay, because we will not precisely determine the location of the change point. What we do is very similar to what people do in time series analysis. In the frequency domain, what people do, oh, we have spectrum, let's take the maximal, and we study the maximal distribution. If the input is Gaussian IID in the frequency domain, it will be independent Gaussian, right? And we take a maximal value, it will follow some Gumbel distribution. Then we can use that distribution to design some statistics to determine if there is an oscillatory signal or not. Okay, many ideas. So what we do is similar. We just choose a uniform grid in the frequency domain, and then we define something called Fisher SST statistic. Why? Because in the spectral domain, analysis in time series is called Fisher statistic. Then we just consider different frequency grid, different frequency, and take absolute value, and then find the maximum. And then we assign A, which is confidence level, and set TA to be 100 times alpha, percentile, or blah, 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 this guy, under a null, and reject a null if Fisher SST statistics of the origin of the signal exceeds TA, the threshold. But this seems okay, right? Because this is somehow we may have interest, right? Everything is a Gaussian distribution. You can take max. So maybe it's something easy we can evaluate. But the problem is, I only told you the existence, the convergence of the synchronous squeezing distribution. And I tell you that, oh, there is a variance, there is a pseudo variance, but I don't tell you what they are. It's too complicated to precisely calculate it. So we do not know the precise value of TA. We do not know it. We need to estimate it. So the question is how to estimate it. So we proposed a local bootstrapping algorithm. That is, first, we have some reconstruction, apply an algorithm to do reconstruction, remove the possible potential oscillatory signal, and get a noise. And from noise, locally, we try to estimate its covariance structure and stimulate Gaussian random process, satisfying the same estimated covariance. And then we apply synchronous squeezing to the stimulated noise for many, many times. And we can generate a lot of synchronous squeezing transform conditional on the noise we observe. Okay, over the grid. Then we can determine the maximum of all this synchronous squeezing over the grid. Now we can repeat this for many times. And we can get the distribution of this M star N L. And the distribution of this set will be something we call bootstrap. Locally we can try to find the threshold. And the theory we proved, showing that actually this bootstrap distribution will converge in probability to the true distribution, which means that we can use this distribution of the bootstrapping data to determine TA, the threshold, and use that threshold to determine if a signal has an oscillation or not. And this is the result. The signal, the short-time synchronous squeezing transform, this is the p-value, and the red one is the threshold we set, which is 0.05, I remember. And you can see there is a very obvious jump here. And then we can make a decision. Okay, over this region, there is really an oscillation, but over here there is no oscillation, and there are some sporadic points that we don't do well, which you can consider to use median filter to smooth it. Whatever, that is the result that you can use synchronous squeezing to do. Then you can ask, hey, come on, you use synchronous squeezing, but you have so many different kinds of short-time time frequency representation, why don't you just use short-time Fourier transform? Short-time Fourier transform spectrogram may also give you a good result. True, it is possible. So we did some comparison. That is from the perspective of power. So you see that if we have a signal which is cosine function, very nice cosine function with noise, then when the amplitude A is range from 0 to 1, what is the rejection rate? Rejection and null hypothesis rate. Then you can see that synchronous squeezing transform can reject almost like up to 85% when amplitude is 0.4. But when amplitude is 0.4, the rejection rate using short-time Fourier transform is only 0.6. Okay? And if you want to go up to 80, you have to have larger amplitude of the signal, which tells you the efficiency of using synchronous squeezing. And if you focus on signal with chirp, that is the signal it does not oscillate with fixed frequency. Then you can see that synchronous squeezing, short-time Fourier transform is further flattened, but synchronous squeezing transform can give you a much higher rejection rate. Okay, so that tells you the benefits of using synchronous squeezing. In the paper, we also compare with other algorithms, for example, some kind of pass per through or something triplet, whatever. I will not discuss it. And I think that is it for today. And I'll see you next week. Okay?